let's move to the third presenter, Pedro Fornaro from UNLP, with the collaboration with COER, and he's going to present a work about advances in co-design of an active mechanical motion rectifier power takeoff for wave energy converters.
This one's forward. Okay, so while we're still preparing this, I would like to start with like a brief presentation. First of all, it's a huge pleasure for me to be here because I have like the opportunity to gather like my past and future together. I'm from Tandil. I'm from Argentina, and then I moved to La Plata, where I studied electronic engineering. Then I also did my PhD there together with Paul Puliston. I can see him up there. And I finished my studies in March this year. Then I had the chance to apply for a postdoc position in Maynooth. And then, well, we know how things ended up being. And so I'm currently also working with John, who is right here. And so, well, to begin with this particular presentation now, as you can see, I'm working with wave energy devices now. However, my background is also on parameter estimation, sliding mode observers, and I also work with energy storage systems. And so I have always been connected with the renewable energies systems, like in general. Why is that? Well, because due to the oscillating nature and particularly lack of unpredictability in the generated energy in general, there's an inherent need of including energy storage systems at some point in the change of production. And what happened here? But specifically, one thing that also happens in wave energy devices is that when we think in terms of controlling a wave energy device, in general, an optimal control law will be also requiring to put back some power into the device that we are trying to control. And so, in general, that energy has to come from someplace. And requiring that energy from the grid is not also like probably the most elegant solution. And including storage systems at some point is also required. So, now, to the topic that has brought us here, I'm working now with an active mechanical motion rectifier. So what is that? Actually, also, as John mentioned in a couple of his presentations, and it has been also mentioned along these past presentations, there's, due to the also inherent oscillating nature of waves, there's a need at some point of this chain that we see right here that goes from waves to the generated electricity to rectify the energy flux at some point. So what we are working with right now is a device that mechanically rectifies an bidirectional, in this case, rotational motion at the entrance of the AMMR, and then we have the output shaft of our mechanical device, a unidirectional motion. Why is that important? Well, mainly because although we have not been working on this topic yet, the generator's efficiency is maybe considerably degraded when its velocity reaches or crosses zero velocity. So if we don't rectify the motion of the oscillating motion of the waves, then the efficiency of the generator considerably drops. So one thing that we might already begin to discuss is how is this AMMR working. So the idea is we would like to rectify the velocity, the input velocity of the AMMR when the velocity here, what we have right here is a flap or a surge converter, which in this case is connected to the seabed. And so the idea is, you can imagine, for the sake of simplicity, that we have a generator connected like at the point of connection, the seabed, so it's turning back and forth, and we have a generator connected there. So the idea would be to connect the device when the velocity is positive, and then disconnect the devices when the velocity is approaching zero velocity. So if additionally we connect a flywheel, like we see right there, then we can help to maintain the average rotational speed of the generator even higher. So, well, this is for the people with mostly like more electric or electronic engineering background. The idea is that, in essence, we can think in terms of this device like a controlled rectifier, in which we have an oscillating motion at the entrance, and then we rectify the output, and we have like rectified unidirectional motion at the output. So here we have an example. It's just a pretty simple example. The idea is, in the upper figure, you can see an example of an excitation force in gray line, and then you can see in blue lines the velocity of the flap in this case, and here we can see down the figure below in blue lines. It's the velocity that is being rectified at the generator. Okay, so it's important to mention that, aligned with many of the topics that have been discussed here so far, that control co-design it's essential in wave energy devices, because we need to change the perspective that we are using in order to reduce the levelized cost of energy in general, to increase or to help to aid to increase the economic viability of these devices, to help to assist to break that barrier that has been constantly holding these devices to reach a commercialization stage. So that being said, what we have right here, and the device, this active mechanical motion rectifier that we are working on, has been developed by people from the University of Michigan in the United States, and we are working together with them, also with people from Queen's University, Belfast in Northern Ireland, and with a group of researchers also from Virginia Tech, which is a company from the US as well. And each one of us has a different role in this project. So the mechanical engineers, particularly working in the US, have developed this device. Here you can see some images, and these images were extracted from this paper you can see right here. But we, as John has mentioned earlier today, we're more focused on the control side of things. And we also have the people from Queen's University Belfast that luckily have like experimental test bench, we could say. They have a tank there. They have very interesting facilities in which we could probably potentially test some of these devices that we are currently working on. So here you can see this would be like a finger of one of the flaps that we're working on. If you imagine like putting many of these together, we could have a flaps together, something like this. It would be. And okay, so, and the name of the project that we are actually working on, it's development, COER project. It's control co-design of wave energy converters. Exactly. Summarizing some, I would love to go into like the specific details of this project. There are many things that I'm very passionate about. Particularly control, stability, and etc., etc. But I would like to summarize some of the most important features that the AMMR could help in aiding this. Some of the well, I wouldn't like to call it failures, but some of the weak points that we would like to address that wave energy conversion currently has. So one of the key points here, as you can see, the first item is increasing the generator's efficiency by increasing its average velocity, as I mentioned before. Increasing the decoupling, this is very interesting because actually, even though we have a generator's inertia connected, because we have an external flywheel in the system, then one thing that happens is that this engagement and disengagement phenomena of the AMMR can help in decoupling both systems and reducing the effect of generator inertia in the produced energy. Increasing power output with particularly reduced reactive power injection. This is just regarding some preliminary results we have found. And also, one thing that is very interesting as well is that we can increase the control design freedom. Typically, in wave energy devices, we have like a direct connection from a device to the controller, and we have a generator torque which may be applied as a control action in the system. However, in this case, we have more control freedom because we can select the connection and disconnection instance in which both devices, the generator and the particular wave energy device, in this case we are considering a flop. Well, in the end, we have these two things that we can design to maximize power output in these systems. So what we are using right now is we need a model. Why do we need a model? Well, from the control co-design perspective, we need a model because one thing that typically happens, as Damien explained, is that we have all the system together. It's like a systematic procedure. It happens that we first design the system, then we design the electronics, etc., etc. And at the end of that chain, someone comes to us, the control engineers, and says, okay, here's the system that you have to control. However, if we think in terms of, for instance, a parameterized model, then we can say, okay, so I would like not only to control some of the controller parameters themselves, but also some of the system parameters. For instance, we would love to change the system's mass, the system's damping, some other coefficients that we might have some power of decision over. And, well, here we have, for instance, this is for the interested people on this topic. I know that there are some people from Plata that is also working in a very similar system. So a very interesting way of modeling the system, assuming that for the time being the AMMR is an ideal device. What I mean by that is that we can think in terms of the rectifier device as an ideal device which can instantaneously and without losses connect and disconnect both systems. Then we can use some tools of the hybrid framework. The hybrid framework is very interesting because we can, it's like an n tuple of variables, some of which are continuous, some are discrete. And so we can model the system very easily using graphs. And then we can also do some other things like analyzing the system stability. And you might say, well, why would the system be unstable? Well, one thing that happens is that when we connect two linear systems via switched signal, it may happen that although both systems are inherently stable, the connection of both might create an overall unstable system. We can also do a controllability analysis. Well, preliminary stability analysis have already been presented at RPIC past week in Misiones, Oberá. It's another workshop that is held every 2 years. And we can also do some preliminary control design. Of course, from the control co-design approach, there is one thing that is very interesting, is that this system includes a flywheel on top of the generator. So we could also analyze the effects of varying the generator flywheel in the, okay, perfect. Depending on the, we may create one thing I didn't mention, but we in general create a cost function that we typically like to minimize or maximize depending on what we are working with. In general, from the control design side of things, we always like to, particularly, this is my case, I like maximize power output. So I would like to skip this for the time being. So to give you an example of the system stability, here we have a flap model like with very simple parameters and a stiffness, damping, a mass. and assuming a proportional integral controller for the system, if we change the connection and disconnection times, assuming a monochromatic excitation force, then we can see that for two very similar times of connection and disconnection, one 58% and the other 60%, one system is stable and the other one it's not. Okay, so one of the things is that that happens in the when we face the control. If we want to face like the control problem, we also need to deal with, as I mentioned before, what can we do with the switching in the system. So we need to extrapolate some of the conventional controllability and stability definitions that we have to include also what happens with the events. So the events would be connecting and disconnecting the system, and we need to create new definitions for those, and then depending on some restrictions that we have in the system, we can analyze if we can if we can sweep the whole state plane, so to speak, because we want the system to be controllable. Very briefly, so in the end, the hybrid framework that we are presenting here is very handy to analyze all of these things that I'm presenting now. So this is very interesting. At some point, the one thing that also happens is that not in every situation the AMMR is controllable. So in some cases, we can see some phenomena that we see right here. Although you remember the first image in which the rectification was kind of like neat and very simple. However, in this case, due to an uncontrollable effect, we can see that we have uncontrolled switches in which the system it's like connected back again, even though we didn't want that. So we need to be very careful with this. And however, having faced those problems, we proceeded to design some preliminary control strategies. For instance, we can think that first the first figure A, right there, we can fix the clutching algorithm. The clutching is the algorithm that connects and disconnects the system, and then design a control algorithm for the generator. We could do like the other way around and fix the control strategy like there, the figure B, in which we fix a simple PI, and then we select and change the switching, the connection and disconnection instance. Or we can think in terms of a global control strategy in which we can actually solve the global problem, selecting both an optimal continuous control and the controller that is also capable of maximizing energy output, considering the connection and disconnection times. Okay, some concluding remarks. Since we are finishing the Congress, I would like to mention some things that are connected with these things that we are. I mean, one of the reasons that it's gathering all of us together right now, collaborative effort is essential. There are many things that need to be addressed in the wave energy community. There are many problems, many devices, as John mentioned. There are many different technologies, and we cannot definitely focus on all of them at the same time. So also dissemination, networking, etc. We need to continuously make effort in this direction. And so I believe that for the time being, that will be all. I would like to especially thank both LEICI Institute and, of course, COER, Damien, and all the organization of this workshop. Thank you.
Thank you very much, Pedro. Someone from the audience?
Well, first of all, your work is very interesting. I have a lot of questions, but we don't have the time here. So, the first thing that I came into accounting when seeing your work, I was surprised by the velocity waveform of the generator. I don't know if you can show.
First one, you said? The first?
Here.
Or I can get it.
Yeah, here. For example, when you have like abrupt changes in the velocity, generator velocity. So how can you achieve that, assuming that you have an inertial, like a flywheel, right? Assuming you have a very inertial load, how can you achieve that kind of steep velocity changes?
Do you have another question you can shoot, and then I can answer both?
No, that's the main.
Okay, so this is an illustrative example, first of all. We wanted to analyze what kind of things may happen in the system. So, for instance, this abrupt change in the velocity that you have right there is not something that we would like to have. Because if something that happens is, if you have the generator rotating with one velocity on one side, you have the device moving on the other, and then you try to clamp them all together, then you're going to have big problems. So, yeah, that is not actually achievable. However, what I was trying to point out here is that at some point you might have like instantaneous connection, even though it was not desired. That is why this was designed for. I don't know if I'm kind of answering you. Perfect.
Anyone else? Quick one. I think that's all. Thank you, Pedro.
Thank you.
So,